And greetings, everybody. Welcome to the Evidence and Reasons for the Christian Faith video channel. It's a scary world out there, and one of the reasons this channel is organized is I think the world is in bad shape and it's going to get worse. Science tells us that the universe will die at some point. Before that, the solar system. And given that we have nuclear weapons now, it doesn't take but a tyrant to really make life miserable here. And sorry to open on such a grim note, but the Christian faith for me offers hope. I'm a we'll go through introductions in a little bit. I'm the owner and founder of the channel. Most of you who watch this know who I am. I'm an independent molecular biophysics researcher. I have 5 science degrees, an MS in applied physics from Johns Hopkins, and also an MS in equivalent in biology and engineering undergrads. And so we're actually going to delve into a topic in young Earth creationism today. I used to be a theistic evolutionist. I nearly left the Christian faith 20 years ago, and I began to just rebuild my faith by studying the topic of intelligent design. Intelligent design is compatible with both old Earth and young Earth creationism, and over the last 20 years, I've felt quite convinced that abiogenesis is a failing paradigm, naturalistic abiogenesis, even though there is credible evidence for a common descent because of the patterns of similarity and diversity and the fossil record for evolutionary theory. That's actually separate from the evolution of complexity. And so there are a variety of old Earth creationists that believe in what they call progressive creationism, where there are miracles kind of interspersed throughout geological history. And because I feel quite strongly that certain evolutionary transitions, like the eukaryotic transition, would require miracles of God. I believe the battle is not really between, young Earth creationism and theistic evolution. It's between old Earth creationism, intelligent design, versus young Earth creationism, intelligent design. Now, this channel is run differently than other YouTube channels that are creationist channels. I had matriculated through secular graduate school. In the process, you learn how much you don't know. And it seems sometimes the loudest voices on the internet, such as one channel that has someone kind of in a Superman getup on his logo. To me, he just has a super inflated image of himself that's not proportional to what he actually knows. He promotes Kent Hovind a lot, whose science I think is just horrible, and I don't think it's appropriate to teach anyone. And we don't do that here. A lot of the audience here that we cater to are graduate students who are, many of them are Christians. Many of them are Christians. Some are old Earth creationists, young Earth creationists, or just searching. And also some professional researchers watch this channel, professional biochemists, professors. I myself have had the privilege to, I've been invited to talk to Christian faculty around the country that are intelligent design friendly. So, my goal is to examine critically arguments on both sides. If people want to know what I think of creationist literature, I think it's been flawed, but I also think the mainstream stuff is flawed, and we learn. And, this is a little bit hard for all the parties involved because, like for me, I've been researching and defending creationism for 20 years. And then I'll invite someone like Dr. Dan here who has totally the opposite view. And we have to try to find a way to agree and learn and come away feeling that we did something productive. So this will not be a shouting match. Some people might find it appalling that I will agree with my opponents a lot. I have said that over the last 2 shows, I think the creationists have made some terrible things to say, and they learn. One of them is accelerated nuclear decay, which I don't think is feasible. And I'm fully in agreement with Jordan on that. but now the question is, we're going to be exploring things like carbon-14 dating. And, there were some things, ironically, as I matriculated through physics graduate school, I began to lean more and more toward young Earth creationism, because there were whispers among the faculty about problems with the Big Bang, and then little things here and there, like my graduate term paper on alternative means of altering nuclear structure. I wrote that in 2012, before we discovered the photonuclear process. Now, I still think that we're not out of the woods as young Earth creationists. We need to have more experiments that would explore mechanisms. I've thrown on the table a very fringe topic, but I think it should be explored. Because the thought that lightning would create neutrons, that paper came out in the 1980s. That sounded outrageous, but then we learned more about it recently. I continue to get reports of low energy nuclear reactions. Like when the granites are crushed, they're able to detect neutrons, which is just like, that doesn't sound like anything I learned in school. And, rather than argue about it, I'm interested in at least hypothesizing what sort of experiments could settle the issue, because that's what's important to me. And so one way I found that we can avoid heated arguments is to say, okay, what experiment or observation would help us maybe resolve the issue, even if it's a repeat of something? Would that help the decision? So that being said, I'm very, very, very privileged to have Jon, who is here. He's a geochemist. And before that, I'll let Jordan introduce himself again. And Jordan, feel free to reintroduce yourself to the audience. We may have some newcomers, and some people may be watching this video for the first time. So thank you.
Sure. I'm Jordan. I am a mechanical and nuclear engineer. And I run a podcast called Reason to Doubt. So I'm an atheist and a skeptic. I used to be a young Earth creationist, but I was persuaded by the evidence that I was super wrong. And I'm always open to new evidence. So maybe new evidence will show me that I'm wrong again. I don't know, but I don't think so. We'll see.
And Jon, thank you. I'm very honored that you would come here. I'm been honored that you would visit my channel and spend time given your position. So thank you, sir. Perhaps you could do the same and just tell the audience what you think they should know about you.
Sure. No, thank you. I really appreciate the invite. I like your discussion format here and your willingness to talk. So really appreciate being here. My name is Jon. I'm an isotope geochemist, well, more specifically a paleoclimatologist, just studying ancient climate change. So I worked in laboratories to study both stable and radiogenic isotopes, specifically to date them, right? I work mostly with the uranium thorium systems, but have used radiocarbon in research. So hopefully I can comment on that, especially, the field and lab preparation and analysis side of things, to maybe clear up some misconceptions about it and try to explain hopefully why we find the anomalies that we do. Science is always more interesting when you get unexpected results, right? Other than that, I've studied the young Earth creationist movement since the mid-90s, I would say. The first geology book I ever read was Monument to Catastrophe by Steve Austin. I've read, the Genesis Flood and countless other books. So I've kept up with it more or less for more than 20 years. For a while, I blogged about it. And so that's the Age of Rocks blog. I hadn't done that in quite a few years, and part of that's just getting back to grad school, finishing my PhD, and moving on. It's so I used to spend a lot more time talking about this and with others. So happy to be here and chat a bit more about
it. I want to I'm going to try to follow through this promise, and I'd like to put your a web link to your blog or any other material you feel is important in the video description, so we can do that, and as a courtesy to you all. Now, just as an administrative thing, I do toss a lot of people from the channel, and I've been accused of cowardice. It's like I just don't have time to deal with certain people, but I do engage the other side, as I'm engaged with Dr. Dan and people that I think, one, I think they had the right qualifications. If people who don't have any biology background are telling me I don't know biology, I'm just like, okay, you don't have a degree. I have a master's and I've published in biology in secular venues. I've worked for genetics for 7 years. If they open up like that, I toss them immediately from the channel. I just don't have time. And I probably block maybe 300 people. If I spent 1 hour dealing with every comment, every person, in a year, that'd be 300 people. And the number keeps climbing. So that's why I'm actually thrilled to have conversations with people that are knowledgeable. And I feel there's an opportunity to learn. The other thing is it's important for me to, if I convey something, I want to make sure that it's as right, that I'm not making any stupid mistakes. I could still disagree with evolutionary theory and say, okay, like when I've had a conversation with Dr. Dan, I say, okay, is this okay? And he'll say, yeah, that's okay. That's okay. And then he'll say, that's where we disagree. It's my responsibility to say, okay, this is where we have a disagreement, and then just leave it at that and say, okay, this is maybe how it might be resolved in terms of an observation or experiment. So that's probably what we're going to do. So to that end, there's the Taylor and Suthan Santos paper, radiocarbon. Are you familiar with that one, John?
Yeah, actually, one of the first articles I ever wrote on my blog was specifically about that topic.
Okay, fabulous.
There we go. Now we have an expert. I'm off the hook.
Okay. Now I was actually backstage. I was about to just charge into this. I said, I really I owe it to my readers because I wanted to cover this so badly. And I said, whether John shows up or not, I'm just going to do it. Even if he shows up late, we'll just do it again because I really
Yeah, sorry to jump in at the last minute. And I have a little caveat. I just got back from Istanbul. Still slightly jet lagged. So if I look like I'm falling asleep, I'm not bored. I promise.
I know you just brought that up, so we'd all be jealous of your jet setting life.
Yeah.
Good on you.
It was really nice there. Gotta admit.
Let's see. Oh boy, my let me know, guys, if my audio is breaking up, you guys on the internet. And so the first thing, now Jordan had mentioned this last week, and I actually read this article and I was so distraught over what it said. I didn't, the few parts I read, I immediately dismissed it and I didn't read anymore. And I said, well, the responsible thing is to double check with experts on this if my understanding is correct. And so we're going to do that now because this talks about, he had a table here. Let me see. It was about the bomb. Okay. So I'm going to bring it. I'm going to put it on the screen. Let me see where it was. I had. All right. I wanted to get the bomb graph here. Boy, this is a long paper. I'm sorry. I had a PowerPoint on this. Did you all find any problems with this, John, on the Taylor Suthan paper?
No, and maybe it's helpful if you don't mind to kind of summarize what their goal was in that paper.
Okay, please speak freely.
Mm-hmm. So think of it this way, like, I don't know if you've ever used a milligram scale, a really sensitive scale. You want to weigh things, right? The first thing you do with that scale is what? You've got a blank, metal plate. There's nothing sitting on it. What do you do before you even put your sample on there?
You calibrate it.
You got to calibrate it and zero it out, right? You got to make sure that whatever it's measuring there is zero, so that when you add 50 milligrams of material, it reads 50 milligrams. And the Taylor and Southon paper, the big thing they were trying to do was take samples that were made of carbon, but that would have no intrinsic 14C in them, and they use that to calibrate or tear the scale, so that when you measure other pure carbon samples, you can compare it against that and subtract those values to know what the actual age is. This is not so necessary if your instrumentation is not so precise. Like if you have older machinery with a low mass resolution or something like that, low sensitivity. But the technology with AMS radiocarbon dating got so good that suddenly the theoretical limit got pushed way back. We could measure smaller and smaller quantities of radiocarbon. And radiocarbon by itself, like it's a very, very rare isotope in the atmosphere. It's not like measuring other systems, like it's not like other radiometric dating systems where it's quite, can be quite abundant even as a trace element. Radiocarbon is extremely rare and it's hard to measure, especially when you're trying to measure something that's, that could be that old, right? So you want to tear the scale, but with radiocarbon dating, you don't actually get to see whether anything's on the scale. So imagine trying to tear the scale, but never being able to see whether it's got something on the scale or not. So what happens here is you're measuring stuff like a diamond in that case, that would be 14C free, but you don't necessarily get to see, like, all you know is the final mass. You don't know exactly what percentage of that could have come from the diamond itself, what percentage comes from other background sources. You can only theorize or use independent estimates of the age of the diamond to determine how much 14C would have in it. So the first thing you should know, if you want to know how much 14C is in a diamond, like they were measuring, the only way to know that for sure is to compare it against a 14C free diamond. Does that make sense? So you have to compare it against a diamond with 0 14C to know if this diamond has any in it. So from the start, I think the use of this Taylor and Southon paper by younger authors has been to say, look, they measured diamonds that got an actual age, therefore there's probably 14C in this, it has to be young. But how do you know there's even 14C in it? Because those are like the metric, this is how we tear the scale, right? And there's no way to know if something has 14C in it or not, because the only instrumentation we have to use is the AMS radiocarbon. But to calibrate that system, you have to use a sample that has no 14C in it. So that's why we have to take something with an independently known age and measure that again and again to see what the natural background levels are when you collect a sample, when you prepare it, when you analyze it, and so forth. And it's important to note, and I think as you pointed out in the video like a month ago, this instrumentation is extremely sensitive, right? And it's so sensitive. I mean, even a blank chamber, if you put no sample in there at all, even a blank chamber will give you a definitive radiocarbon age.
Right? Well, I want to thank you for that introduction. That explains a lot. I played this video. I'm going to play it again just so people can see how an AMS system works. And you've given me insights into what they were attempting to do. Okay. So that was very helpful to understand. I'm going to play this, even though I played it before. I think it's important because I'm going to refer to this AMS system in each of the parts, particularly the isobutane counter. So let me fire this up. Oh, by the way, now I remember what I wanted to say. If you saw me looking here, I didn't mean to be rude. It's just while you were talking, I was trying to set this up. It wasn't that I was not listening to what you had to say. No. So because I have to run the controls, I don't have someone to say, I could just kind of point.
Yeah, one-man show.
I have to do this all myself. So I hope you'll forgive me, and the audience, I hope they'll understand when you see me kind of doing this. I have 3 monitors and all these controls to run at the same time. So let me just fire this up, and let me know if you get people in the chat. Let me know if you're getting audio when I play this.
The AMS itself, an accelerator mass spectrometer, has really three components. One is called the low energy end. Let's take the example of carbon. And radiocarbon is present in the environment at 1 million millionths of an atom. So it's a very, very trace isotope. So what we do is we take any sample, we convert it to graphite. There's a little aluminum button with the graphite in the center of it, and we can mount up to 200 of these graphite targets into a cartridge type, we call an ion source. Because what we're going to do is take the atoms of carbon in that graphite and convert them to ions. We're going to ionize them. Once you get things ionized, you can move them because we use electrical fields and voltage fields, voltage gradients, magnetic fields to move these ions around. So we're going to create an ion beam. So it's a beam of carbon racing out of our source. We bend that beam around with magnets and electrostatic devices and aim it into a big tank. So we're looking at a tank right here. It's a T-shaped tank filled with an insulant, sulfur hexafluoride, because we're going to create a huge voltage in that tank. And so it's like a big transformer that you see in hydro systems, except ours is 3 million volts. So we're going to race those ions towards that positive pole, and then we're going to switch them. We're going to strip those electrons off carbon and turn it to a positive ion just as it hits that positive pole, and it's going to shoot them out the other end. Now we're going up to a few percent of the speed of light. So our ion beam is really rocketing. As we're walking over here now to the west side of the machine, we're at the high energy end. So our ion beam is racing out as a flight path goes into a magnet. And we've got a few control centers along it. These are electronic lenses, so we can change the shape of that beam. So now we're looking at a magnet. It's actually the big, what we call the analyzer magnet. It's 18 tons at whack of energy because we have to bend that beam at 90 degrees. And so we've got just pure carbon coming down there, but carbon has these isotopes, carbon-12, and then carbon-13 with an extra neutron, and carbon-14 with an extra 2 neutrons. And that's the guy we're looking for. So as we bend that beam, the lighter isotope, carbon-12, bends the most, carbon-13 likewise, but carbon-14 continues on, straight on down that pipe. So we're going to now count, we're going to measure the strength of the carbon-12 and the carbon-13 beams, but carbon-14 is a very weak beam, and we can't measure its strength with current. We have to actually count the atoms of carbon in that beam. So at the very end, we have a detector filled with a gas, isobutane, and the carbon-14 atoms come down and collide with those with the isobutane, and they give off their energy. So this is a high-speed collision. All that energy is dissipated, and each time there's a collision, we measure that energy. So now we come up with a count, and the number of carbon atoms is compared to the carbon-12 that we measured, and that tells us the concentration.
Well, I hope everybody, especially in the audience, enjoyed that video to understand how this radiocarbon is being counted, the radiocarbon 14. I did mention last week, and I'll mention it again, some young Earth creationists have friends in the accelerator mass spectrometry discipline. And you could see like the three lanes, the carbon-12, the carbon-13, and the carbon-14 lane. Some have, I think, and I only got this in a passing discussion, but hypothetically, you could collect the carbon-14 and 13. That would be a true blank in the truest sense. If that ends up being a good reference point, and I'm really sorry that I don't know where this conversation happened and where it happened and all the details of it. Maybe it's just as well, because if it's a secret project, that's something we have to be careful about. But I would just say, in principle, I think that would be an experiment worth running, because then we could actually see then if we actually have a true blank to calibrate it with, versus trying to use the what the young Earth creationists feel are already things that inherently have carbon-14 in them, and they can't really be a true blank. So there has been discussions in the young Earth community to create a true carbon blank. And as far as I know, this AMS system is the best. There might be another method. There are discussions now to create that calibrating blank. Now, I will mention the isobutane. Butane has carbon in it. It has modern carbon. And the way that I felt that this counter worked, it really didn't matter whether it had carbon-14 or not. It's the fact that it would just react to this high intensity ion passing through it. We have like cloud chambers, for example, that can detect energetic charged particles going through it. So I don't think that modern carbon would be a source of contamination in the isobutane detector. If anyone disagrees, just this is the forum to discuss it.
I'm leaving that to you, John. You're the.
To me, it doesn't sound practical to me, but again, you're dealing ultimately with real geological samples. And I mean, again, anything you measure, and this is the tricky part of AMS radiocarbon, anything you measure is going to give a signal suggesting that you have 14C in it. So the goal of AMS is to figure out just how much of that comes from the background noise or contamination introduced, et cetera, so that you can get more precise ages the farther back you go.
Isn't if I recall correctly, it's like measuring the mass, right? And so if you had another mass 14 atom that somehow got through, that could detect as as 14, which they would interpret as carbon-14, right?
You have several isotopologues. For example, when it's measuring, you could have a 12 carbon attached to a couple hydrogens, or a 13C attached to a hydrogen, or a nitrogen particle in there, something else like that. These all have slightly different masses. Even though we call them mass 14, they're slightly different enough that the mass resolution can detect the difference between those, but there's always some interference. So even if you had like an absolutely pure, just in imaginary world, nothing but 12C atoms and 13C atoms, you would still detect on your AMS instrumentation, you would still detect 14C, even though there's no 14C there.
No tool is perfect.
How could we get nitrogen? How could we get enough nitrogen? Okay, I get your point.
Well, there's not. What's the atmosphere made of?
Well, I looked at it said there's a vacuum lock where you're throwing the ion beam. So I'm imagining you're pulling this off.
But there's no such thing as the perfect vacuum, right?
Okay.
And there's also what's called like a memory effects. So stuff that literally gets stuck in the vacuum tube and then it gets released after you're measuring the next sample. This is something you have to be careful about, especially if you're dealing with, if you're looking at stuff that has like thorium in it, or it can get stuck to, I don't know, organics or oils or some other vapor. It gets clogged on the vacuum tube, and then it shows up in your later samples. And you're like, gosh, where did all this thorium come from? And you got to clean out the system, and it can get really messy. So even as good as the instrumentation is, that doesn't mean you could ever achieve things like a perfect vacuum, or entirely get rid of things like magnetic and electrical interference or memory effects and so forth. So this is something always to keep in mind. There's always what's called a model age given by the machine, even if you're measuring nothing but a vacuum. And because of that, it's not surprising to anybody that you would take a sample of diamond, a sample of 300 million year old coal, and put it in your system and get a real radiocarbon age. There's no reason not to expect that.
Okay.
The challenge is figuring out how we can take stuff that really is less than 100,000 years old and date it accurately.
So, okay, I think this is news to me about the nitrogen 14, but that actually sounds really good. So now I will. That being said, so I'm noting. I think that's a very credible point right there. So the audience, the nitrogen contamination, I consider credible. Please go on.
Oh, I was just going to say too, the best way to figure out the difference between a real signal and noise or consistent background, something like that, is just to take lots and lots of samples and measure them again and again. And going back to the Taylor and Southon paper, what they did, one thing they did, they took a single diamond and they split it into 6 pieces and they measured the date. They put each of those 6 pieces in the machine to measure the age. And all of those ages came out exactly the same, right around 78,000 years or 77,000 years, something like that. They all showed that, I mean, it's a false radiocarbon age, but that was what they showed. And so that tells you that in a very pure diamond sample, you can get a consistent background. And so you know how much to subtract, like 75,000 years, that's the same as 0 radiocarbon in the system. So we can just subtract that signal out to know that that's like the ambient background noise, so to speak. We have to tear it out. So when you remove that, you can more accurately, well, theoretically, you can more accurately date stuff that approaches 75,000 years in age.
Okay, so I'm going to go to the Taylor and Southern paper here now. See if I can bring it up. And I'm sorry for the font. Since you all are familiar with it, unfortunately, the audience may not be, but I can't get rid of this part here. I'm trying to get rid of the...
I think that's the toolbar. I think if you hit tools, I think it goes away.
Tools. What did I
do? Yeah, if you go into your PDF again.
I'll go into the PDF again.
Okay, there on the right side of your screen, above the thing you want to get rid of, there's tools, sign, comment. If you click tools, I think it goes away. There you go.
Oh, you're a genius, Jordan. Thank you.
That's why they pay me the big bucks.
Yeah. Okay. One of the I'm just going to read this just so because I'll mess it up if I try to summarize it. One of the principal challenges in obtaining natural carbon-14 measurements is the result of very low concentrations of natural carbon-14 in organic samples at the level of about 1 C14 atom for every 10 to the 12th. That would be a trillion carbon atoms in modern organics. There is also artificial bomb C14, which was produced during the detonation and testing primarily of thermonuclear weapons in the atmosphere beginning in the mid-1950s and accelerating in the early 1960s. The potential implications of the existence of bomb C14 for our topic will be discussed below. Any type of technology designed to measure natural C14 levels at a reasonable level of accuracy and precision is confronted with the task of identifying measuring pulses, typically in an electronic circuit, which usually indicates the presence of C14 in a sample. In AMS technology, the signals from non-C14 mass 14 particles, such as the most plentiful isotope of nitrogen. So it was there. I'm sorry, I missed it earlier. So thank you for correcting me on that, John. Or mass 14 molecules such as CH2. Now, I have a problem with that. Didn't we ionize this? I mean, it's supposed to strip this off. So I'm in agreement with CN14, but
yeah, it does ionize it. So that CH2 that does have a charge to it, it is ionized, but it's the whole molecule that's ionized.
Right, and I think if you count it up, yeah, you're right. Sorry, let me stop talking.
Well, I mean, when they ionize it, they don't put it in the plasma form, do they? Because then it'd be stripped of electrons.
Right. It uses typically they'll use something like a cesium beam, just like taking a much heavier particle and just hitting it against that, and that's what shatters it off. So when you use a beam like that to vaporize your sample, then you can, sputter off little pieces of, in this case, 12CH2 or 13CH, something like that. And so it is ionized, it's missing electrons, or something like that. So it is a charged particle, but it's a full molecule that goes through the system. And these are extremely rare. It's not like this is like these mass 14 particles are giving you a young radiocarbon age or anything like that. It's extremely small, but it's just enough there that it could never be zero. You could never measure zero radiocarbon.
Okay, thank you for that. It's just that I don't know how a carbon could bind to hydrogen if it doesn't have any electrons in it.
It does have electrons. It's just ionized where it's got a charge of like 3 or something.
Okay, +3. All right.
So not fully ionized, but some ionized.
Yeah, it's not like a plasma form the way that you would have in a ICP-MS, for example.
Okay. Would be multiple orders of magnitude more prevalent than C14 if it were not for fortunate circumstances that would be explained below. Clearly, natural level of C14 measurement technologies used for dating applications must deal with highly disadvantageous signal-to-noise isotopic ratios. All right. It is critical to and I'm sorry if I'm just belaboring this. I'm just trying to be thorough here. It is critical to an understanding of the issues raised in this paper to realize that all AMS systems measuring C14 concentrations together with all other analytical instruments designed to obtain precise quantitative measurements of physical entities such as isotopes, elements, or molecules share a well-known characteristic. This characteristic is referred to by somewhat different terms depending on the specific technologies employed. In the case of the methods used to measure natural C14 concentrations, the term is background. Okay, so natural C14 concentrations, it's background. In some contexts, the term blank, as in machine blank or sample blank, is also used. In an instrument system designed to measure natural levels of C14, a background or blank is the product of some pulse or signal appearing in an electronic circuit, which typically indicates the presence of C14. In fact, indigenous C14 contained in the given sample can be reasonably assumed not to be present. Okay. And I'll just read this. So that the point just made will not be passed over quickly, let us reiterate the statement at the end of the previous paragraph. Every sensitive modern analytic instrument of which we are aware, no matter what type of physical entity such as an instrument has been designed to measure, exhibits some type of background or sample machine blank signal. There is, as far as we know, no exception to this statement. In the remainder of this discussion, we'll use the term background to encompass all these types of signals. In C14 studies, a sample used for background measurements would be an organic of sufficient geological or paleontological age that it can be reasonably assumed, given the C14 half-life of 5,700 years, all of the sample's original C14 content should have been reduced to 0. Okay, and that's the young Earth creationist complaint, is that there is an assumption in the blank already. Okay, so it could have C14 that was originally there if the Earth is not, if most of the samples aren't really truly blank, then that's what we're picking up. So that's a point of disagreement, just pointing that out. Examples of the types of organic used in C14 as infinite age or background samples would be fossil organics of various types such as coal, natural gas, petroleum products, as well as geological graphite and Mesozoic age limestone. We might also note that questions have been raised regarding the use of coal samples, which have been contaminated with organics more recent origin as the result of presence of various types of in situ microorganisms to serve as background samples. And they cite Lowe 1989, and I actually cited that last week. That's an interesting problem there, and I'm going to skip that for now. It's subject to a later discussion. Lowe 1989. Others report that if adequate chemical pretreatment methods are rigorously and consistently employed, the problems reported with coal can be resolved. And Santos was Santos 2011, and Santos is the a co-author here. So, all right. Now I'm going to go to the bomb part. Let me look for the word bomb. Okay, it turns out that C14 activity of contemporary living organics obtaining their carbon directly or indirectly from current atmospheric or biospheric levels of C14 cannot be used to define zero on the C14 timescale. This is due to the impact of combustion of massive amounts of fossil carbon and more recently the production of artificial or bomb C14, primarily because of these two human-caused effects on contemporary C14 levels. Modern or zero-age carbon 14 content has to be redefined as a percentage of C14, C12 ratios exhibited by specially prepared standard samples, which are used by C14 laboratories to determine modern. For additional, okay, I get that. The second type of modern environmental contamination samples is that of bomb C14. The term bomb here refers primarily to the effects of thermonuclear weapons detonated in the atmosphere by the United States and Soviet Union until the 1963 Partial Test Ban Treaty went into effect. One result of the detonation of these devices in the atmosphere was the production of large fluxes of neutrons, in turn caused production of significant amounts of artificial non-cosmogenic bomb C14. The maximum amount of this artificial C14 was present in the atmosphere and thus was also contained in living terrestrial organisms in 1963 in amounts that resulted in almost doubling the amount of atmospheric and biospheric C14. By referring to Table 4, we see that the addition of 50 parts per million of modern carbon, or about 25 parts per million 1963 bomb, would result in having an organic sample which originally contained no C14 exhibit a measured C14 age of 80,000 BP. What does BP stand for?
For present.
For present. But it's important to note that present means the year 1950.
Because we can't
present.
possibly have it be simple, right? You know.
Yeah. Well, that's because this was developed right around the 1950, right?
Okay, I'm going to read this again so I could just digest it. We see that the addition of about 50 parts per million of modern carbon, or about 25 parts per million of 1963 bomb, would result in having an organic sample which contained absolutely no C14 to exhibit a measured age of 80,000 before present. And I've got a real problem. That's where I had a real issue. How did this, let me take this down here. I mean, that's affecting the atmosphere, but anything that isn't, I mean, if we have an isolated sample inside, let's say some vault, hypothetically, far away from the nuclear blast, how's that going to get any of the atmospheric neutrons of C14 in it? So something is blank, unless you're somehow mixing it with the atmospheric
well,
carbon.
that's the thing. You are mixing. It's not isolated. Like, I don't know, what sample do you want to use? You want to take a diamond that was collected. Like, you collect the diamond in the field. It's exposed to the atmosphere on the way to the lab. It's exposed to the atmosphere until you put it in that chamber, and then you vacuum down the chamber. But atmosphere can still adhere onto the surface of the diamond. And also within the vacuum tubes, it's never a perfect zero vacuum. So you'll always have some, even if it's absolute trace amount of atmosphere inside there, there's going to be, it's not zero. It's never absolutely zero. So that's where it comes from.
I think something that's important to keep in mind, just for people who aren't familiar with how these measurements work, though, is it's the amount of that you're adding is very small. So if you had something that dated to like 10,000 years ago, like the signal would be so much larger than these sources of error that it wouldn't be. It's not like these sources of error are going to take something from, it says it's 10,000 years, but it's actually, I don't know, thousands of years off of that.
No, this is where I wanted to work through the calculations, because when I worked through it in my head, I dismissed that instantly. So let's say, how big are the samples that are put in an AMS system? How many grams of carbon
Like
graphite?
1 to 100 micrograms.
Okay, all right. 100 micrograms is how many? Help me with my math here. How many grams would that be? Point.
Like
Well, microgram would be 1/1000th of a gram, right?
Okay.
So 100 micrograms would be 0.1.
Okay.
Right.
Or
No, sorry, I'm thinking milli.
Mhm.
Take it back 3 more orders of magnitude.
100. So 10 to the minus 6 to 10 to the minus 4th, that would be 1/10,000th of a gram.
I had this, yeah, so 1 to 100 micrograms is kind of standard. I had a source that I was looking at earlier. I just wanted to double check that. So that's correct.
All right. So,
and that's the problem with the AMS. You're using such small samples that it doesn't take much contamination to add a real age, like an apparent age. And that,
right.
that age of 70,000 years, that's equal to about 1 in 40 quadrillion of the atoms being 14C. So if you have 40 quadrillion 12C atoms in just one that's 14C, that's an age of 70,000 years. Just to give you a sense of how little you need.
So it's a little, you've given me an important data point here as far as 1. So it could be 1 microgram, which is very small, to 100, which is a little bit bigger. So when they are measuring a diamond, they don't actually blow apart the entire sample. Is that correct?
That's correct. Yeah, that's right. And you could put more sample in, and actually it is better to put more sample in. They're kind of testing limits if they're only using a few micrograms.
Okay, thank you. All right, so I looked at the percent carbon dioxide in the atmosphere. I got a figure of 0.04%. Now, 1 mole of substance, 1 mole of gas under standard temperature and pressure is 22.4 liters. So, I'm just going to use one. I'm just going to use 1 mole of carbon because it's just easier to work with, which would be roughly 12 grams. It's more like 12.1 grams to get 1 mole of carbon. If we had a graphite sample, 12. Okay, so 1 mole of that, you would need 56,000 liters. So you divide 22.4 divided by 0.04. You need 22,000. You need 56,000 liters, and somehow you would have to translate all that to be able to raise the if we wanted to put all that on the carbon blank, then we could raise it to, I guess, 50% modern carbon. But the point of this is if we actually calculate the physical number of moles of carbon in your sample and compare it to how much your vacuum is, that would be an observation I would be interested in to do that calculation, because we can invoke. See, that's why that figure of the 50 parts per million with the bomb, I'm just like, how could that get in there? Did anyone actually go through? I would like to see the numbers calculated of how much they think is in that vacuum chamber compared with the sample. So if you have a microgram, that would be.
What that means though is if you have, say, 1 unit, whatever the mass unit you want to use, if you have 1 mass unit of your sample, 25 parts per million would be bomb spike 14C added to that. So it's just a fraction of a percent that's being added to that to give that apparent age. Does that make sense?
Well, see, where this would be, an issue is if I've heard we've gotten some diamonds that did register under 40,000 years, say 35, and also things like the collagens at 34,000 years, that would mean it had like 5%.
That's quite a bit more.
Yeah.
But the problem is when you're dealing with different substances, the background's going to be different.
Well, I'm talking, I acknowledge that point, but the background, I'm talking about the atmospheric effect here. The atmospheric effect cannot, I would find it highly dubious to think that could be counted against some of the collagen measurements that were returning 5%.
No, in that case, I wouldn't think that that's going to be a major factor.
Right. Okay.
No, but you got to keep in mind, like there's a whole string of things that have to happen, and every step can potentially add some sort of contamination. Every step could potentially add some background. So that's why they measure different types of material to sort of mimic, take 14C free materials and mimic the modern stuff or recent stuff that we're actually dating, because each one will have different interactions. So if you take a piece of peat, a layer of peat, so just like dense woody vegetation, right, in the sedimentary layer, and you want to date that, first you got to collect it. In that peat itself, it's, you got the carbon that's original to the plants, but you also have things like groundwater, microbes, etc., that are mixed in with that, so you've got to clean it off. So the process of treating it with like acid-base oxidative agents like this, it removes that contamination, but it's not perfect, so there's some left from that. Mixing with the atmosphere, there's a little bit left from that. When you convert it from whatever it is into graphite, because you don't put a piece of coal or wood or anything like that into the AMS machine. It has to be converted to a pure carbon substance like graphite. So the actual conversion, the combustion reduction process, introduces potentially some more. Not a lot, but it's just enough to give false ages of, anywhere between 40,000 and 70,000 years. And then there's the issue with like the electrical noise, the not a perfect vacuum, even things like using the grease around the O-rings could introduce organic particles to the system and register just a little ping here and there that makes it think it's detecting 14C in your sample. So if you take all of that together, it's quite easy to see why those collagen samples, which are not really collagen, by the way, could have an age of 30-something thousand years.
What's the detection limit for? You mentioned we talked about you were in the side chat when we were talking about Geiger counters. Is it about 18,000? I mean, it's been a long time since anyone's used Geiger counters, but I guess because it's cheap.
That depends on the other setup and how well you can account for background radiation, because in that case, it's becomes harder to tell the difference between other types of beta minus decay. And we can, if you can measure the actual energies of all those counts, then you can distinguish between what's beta decay from potassium and what's beta decay from carbon. That's easy to do. Only if you have enough counts and you could measure the intensities and the energy levels. So it depends on the system setup. I mean, this is a reason, though, that you tend to date stuff that's less than 50,000 years. So you don't have to deal with these issues because they only show up when you're getting into stuff that's potentially beyond that limit. One thing I would point out, though, again, replicability is the best way to look at that. And so I don't know if you have the Taylor and Sithon like 2007 paper where they're looking only at diamonds. If you have that handy.
Oh, so this is a different paper. No, I'm sorry then. This is the one that Jordan sent me.
It's okay.
I didn't realize there was another Taylor.
But there's the one where specifically they looked at diamond samples, and as I mentioned, they took a diamond and split it into several different pieces and measured the different pieces. And the ages they got were very close to each other. But one thing that I've pointed out too is that the delta 13C ratios are completely different in each face of the diamond. And one way to know that whatever 14C is apparently being measured here is not from the diamond itself, is to see that the 13C ratio goes all over the place in each face of the diamond, but the radiocarbon age stays the same. And you have to ask the question, like, let's say, just for the sake of argument, let's say that...
No, that was really good. Can you repeat that? That was really good. So you're saying...
So this is table 2 in Taylor and Sithon 2007, where they're actually measuring diamonds.
And they're talking about the C13.
Yeah, so there's always measured 13C and 14C in the sample, and its relative abundance.
If I could beg either one of you to send me that one too, I would like
Sure.
to look at it. That would be very valuable. Have you read that one too, Jordan?
No, I haven't.
That's okay. I'll send it to both of you.
Sweet.
So what I was saying though is in those diamond faces, they always measure 13C and 14C because technically we add a correction based on the 13C abundance because this deals with the original mass fractionation of how much 14C was incorporated into the original substance. That's like a side. I don't want to go into that because it'll take like I think an hour or more. Okay. But just for now, let's say that 13C can tell you a bit about the process by which this substance formed or the sources it came from. So if you have organic carbon, if you take the organic carbon from the average biosphere around the world, it's going to be about minus 25 per mil depleted, compared to, say, limestone, which would be like 0 to 4 per mil on average, versus volcanic carbon dioxide, which is like -5. And so different sources, different materials have different ratios of 13C to 12C in them. And these diamond faces had very different 13C values, which could be explained a couple different ways. One in how the diamond formed or the sources of carbon it had. And so I'd have to ask this question.
Sorry, that just blows my mind. You're saying that the limestone versus like organic materials has different ratios of carbon 12 to carbon 13.
It does, because when that organic, to get the carbon into organic matter, it begins with photosynthesis, right? And photosynthesis takes carbon dioxide out of the atmosphere, but it doesn't take every isotope in at the same rate. It takes in 12C slightly faster than it does 13C. So organic matter has less 13C in it than
okay.
Rocks.
This is Jordan. That's just a cool fact.
It also means it strongly prefers 12C over 14C. So plant material takes in less radiocarbon than something like inorganic calcite.
Well, so this is the first. I don't know. That just blows my mind. That a living system can discriminate isotopes.
It discriminates. Well, you do know how. The formula for like mean velocity of a gas based on its mass?
Yes.
And so the mass, the heavier a substance is, the lower that mean velocity is, right? So basically, the heavier carbon, the 14C, if it's part of a carbon dioxide molecule, is slightly heavier and it travels at a slightly lower rate, which means it has a harder time statistically speaking, it's less likely to go through the cellular wall and get incorporated into the photosynthetic process. So this is a mass-dependent fractionation based on diffusion through a fluid boundary.
Actually, you've just given me... This was worth the whole discussion right there.
It is.
Okay. Did you know that, Jordan? That I didn't know that.
I'd heard that before, yeah.
Wow.
But let's put this to the test. That means if you just give me a sample of carbon, just measuring the 13C to 12 ratio, it can tell you probably whether it came from organic origins, from some sort of life form, or whether it came from, limestone from the ocean, or whether it came from the atmosphere or something else. And so in these diamond samples, like I said, it's all over the place. You've got some that are close to organic values, some that are close to limestone values and mantle values and everything in between. Now,
so, I'm sorry, before I... okay. please go on. I'm going to try to hold my thought before I forget
Well,
it. So
okay, so
please
here's
go
a
on.
simple, let's say for the sake of argument that these diamonds that are showing an apparent radiocarbon age, let's say that that 14C is actually part of the diamond, and that, I don't know, you think somehow this means that they're younger than we think they are, that they must be young enough to still have 14C in them. That's kind of the young Earth argument, right? So let's just, for the sake of discussion, let's grant that. And let's assume that all that 14C actually came from the diamond itself. Well, where did that radiocarbon come from, do you think? In like a younger scenario, where did it even come from?
That is the topic of what I consider the low energy nuclear reactions, and which I'm acknowledging is fringe, and Jordan and I have acknowledged that it's fringe, but this is, I'm beginning to, like I said, when the whole thing about photonuclear processes said, okay, there's still more to learn about how things can emerge. And I've been impressed with some of the experiments done with compression of granite beyond a certain mechanical strain. And I'm not a mechanical engineer. They're detecting neutrons and also transmutations. Now, I hate the word cold fusion because I don't think anyone knows what the mechanism is.
Well, to put that in simple terms, so is that to suggest that you think it could come from, I don't know, somewhere in the mantle itself where the diamond formed?
I don't know. So
because otherwise the carbon, like if 14C is produced in the atmosphere mainly, right? And the question becomes, how did that 14C from the atmosphere get down into the lower mantle where a diamond was forming?
Right.
Especially within the last few thousand years.
No, these are totally legitimate questions. And I don't think, I'm just throwing this out there that for the young Earth creationism to move forward, we're going to have to actually depend on people that are not young Earth creationists, which are the...
Well, I asked this question because like...
the low energy nuclear community, and that is very fringe, but I haven't given up on them. Okay.
I think you should probably give up on them.
No, I'll tell you why. Okay. To be fair, I'd say they have a better chance than people trying to prove abiogenesis or eukaryotic evolution, because if we just use basic science, abiogenesis, researchers, secular, peer-reviewed, both in the Proceedings National Academy of Science, in Nature, they're invoking multiple universes to solve the problem of abiogenesis. I said, okay, at that point, you're invoking the equivalent of miracles. I think that low energy, if the mainstream can invoke mechanisms like that, I don't think young Earth creationism or low energy nuclear reactions is any more outrageous. That's where I'm at. So, it doesn't sound, to me, what sounds fringe is abiogenesis and eukaryotic evolution, because it's a similar statistics. But, well, thanks for airing your opinion there, Jordan. I know you're really skeptical, and it won't be resolved until the low energy community delivers. So I will concede that for now.
So speaking of stuff forming carbon-14 underground, you want to talk about that? I don't know if you're done with the...
No, because I had one point I wanted, and we can move forward because you invested so much time. I hope you didn't mind, Jordan, because I wasn't expecting Jon would join, but I wanted, while he's here,
I didn't mean to take up so much time too, talking about all the little details here, and because I know you wanted to get to Jordan's thing.
We'll cover as much of Jordan's work. I think it was excellent work.
I'm not doing half of it. If you don't have time, I'm not doing it. We'll do it another time.
But I wanted to say, you gave me a very interesting data point. So you're saying limestone. So we could take limestone. Could we distinguish it, like, say, from a clamshell in terms of C13, C4, C12?
Yeah, it would have the same ratio because that's what the clamshell is made of. But the actual organic tissue, like the muscle and the fat and all this, like this, that would have the low delta 13C value.
Where could we? Okay, because I thought that one thing the young Earth community has said, limestone, it's CaCO3 or something like that. I don't know the formula. It doesn't necessarily have to have an organic origin. That's why we think the limestone actually has very low blank, we can actually take some limestone that looks that does, we have clamshells that are from the Cambrian that date it like in the 24,000 to 30,000 age.
Well, I would be quite skeptical of that.
I know, but because I've been asking around, and and other people have pointed out the limestone does not have that that recent an age. But I do have to contest something that you said about the collagen. I don't think that the bomb C14 could account for the background, creating that detection of.
Well, if you're doing these measurements in the 60s when it was really high from the bomb spike, then that's what they meant. But the atmosphere has since, lost a lot of that bomb spike, so now it's come back down again. That they just use those two.
But I don't see how that could affect. Okay, so so the question is, do we think it had an atmospheric effect that somehow got in the vacuum and is in sufficient quantity to give us a measurement of,
Well, we know that for every single sample, there's going to be a non-zero contribution from the atmosphere.
Well, the thing is let's say we're sending stuff to the same AMS. Some collagens date with much less, and some with so like that, the 30,000, I think it was 34,000. That would go. I have it here on my calculator. That'd go through about 6 half-life cycles, not quite 6. That would yield 1.6% modern carbon. And I thought I saw a number more like, I don't have the paper with me, I'll double check, that it was a much higher percentage than that, like say like 3%. So that'd be under 30,000 years. So 3%, I don't think this, how can we get collagens that register 3% and then some that measure much, much less than that?
Yeah, so this is a good point. What I wanted to bring up about replicability.
But it's a different collagen. So replicability, we would take the same collagen samples and then run it through the AMS several times. Was that where you're headed?
Well, so I've seen those, the tables where they claim to have measured or radiocarbon dated collagen or bone material or other things. And
but by the way, I have to contest something else you said. You said it's not really collagen.
No.
We use mass spec to determine that it's collagen. We can do mass spectroscopy on it.
But it's not.
It is collagen.
That's not how you would determine that it's collagen. Because it's going to give the same values as other organics and such.
Well, there's okay. How would you determine that it's collagen?
To determine it's collagen, you got it. Well, sure. If you separate it and you have a sufficient quantity to
like if you use a gelatinization process, would that be sufficient?
I mean,
that's how we make Jello. That's how we make Jello in the food products.
Well, first, just to clarify, which kind of collagen are you talking about here? Is there a specific sample you're talking about, or?
The ones from dinosaur bones?
Yeah. So
I don't have the specific species.
There's not been isolated collagen from any dinosaur bones. What they find are degraded remnants that are...
Graded what?
Degraded remnants that are derived potentially from collagen in dinosaur bones, but there is no actual collagen in it.
How do we know that?
Because it's got a completely different molecular structure. So it's related. It could decay from that or degrade from that, but it's nothing like original collagen. And it's never been separated in sufficient quantities where you can say look, using the mass spectrometry and the magnetic resonance spectroscopy and so forth, it's never been isolated where you could say, yeah, this is a complete collagen molecule that came from a dinosaur bone, let alone in sufficient quantities to radiocarbon date. So what happened is they said, here's a bone, isolate the collagen. They applied the same chemical techniques that you'd use to separate collagen in modern bones. And that doesn't mean what you ended up with is in collagen, is actually collagen, because the lab doesn't actually test that before they run it. They just apply the separation techniques to the method that they have. And if there is no collagen there, then you're going to end up with something that's not collagen. And so that radiocarbon date is quite meaningless.
So how did Mary Schweitzer get a sequence, that fragment sequence?
That's what I was talking about. It's not actual collagen. It's like degraded remnants of it. So it's like organics that have been, broken down quite substantially. And based on what she found, it might be related to collagen that was originally in the bone, but it's not anything like the original collagen.
Do you know how that determination was made to get that sequence? Because these
I don't. No, I wouldn't be able to tell you in great detail about that.
So if they determined that these, so I would ask, the thing I need to ask is, how did they determine that these are the peptide bonds between the amino acids and that they got these fragments? Because I actually did look it up in the NIH database, and I can actually get hits on the sequence she published. So I'm going to have to try to find out how we know. So this is the first that I heard that you're saying it's not real collagen.
No, it's not, and that's in the papers itself. And they talk about the methods that they used to isolate what they thought were, remnants of that, and it just got lost in the terminology, like the when the papers were kind of simplified and in common terms, people heard collagen and they just kind of assume it's the same thing as collagen that you'd pull out of a modern bone, and it's absolutely not. It's got carbon in it. It's got similar bonds and stuff, and so what they're trying to argue is that it's remnant or residual from that. In any case, the stuff that didn't radiocarbon date anything.
I would still consider that legitimate, though. If you have something with a peptide bond, that's very rare. You don't find that in nature.
Well, so sure, but
if you're extracting something with peptide bonds, that's the original carbon from the original fossil.
It is something that's like. Again, it's in such minute quantities, and it goes through such a long chemical treatment process that the actual carbon that could possibly be from that original collagen is this much, and everything you added to the system is this much. So if you try to radiocarbon date that, even if you could isolate it, which you can't, it's going to be meaningless, meaning it will have nothing to do with the actual carbon that was from any organics in that dinosaur bone.
No, and so I have to challenge that, because until we're actually counting the number of molecules, and this would be the way to actually say, okay, this is how much we can expect. If we have something with a peptide bond, how much of an impurity would actually affect the age? I don't see those calculations done by anyone.
How much of an impurity would affect the age?
Yeah, well, we can't just say little, because I just gave an example with the C14 bomb thing, and I was saying, no one's working this out that they could actually say, oh, we have a little bit of atmospherics in here that could affect the age. No one has actually worked out the number.
They have worked that out, and we could work. I'm going to try to avoid doing math right now, so I'll be happy to discuss it if you give me a chance to look it over. And I want to try to do that on the fly. But yeah, that absolutely has been working. It's quite easy to calculate, and when you have those minute quantities of sample, then the ratio of potential contaminants from your treatment processes that just swamps the signal. So what you'd actually be measuring, you couldn't tell the difference at that point between what you've added to the system and what might have been original potentially. And when you look at those,
I think it is too much. Yeah, it is too much to ask to do this on the fly. But I'm laying it out what I think has to be done. Because I don't find it believable that that you could add 3% modern carbon contamination. You'd have to be really careless, and that would also take place in terms like when sawing bones, or like say we're cutting through marble or something like that, and then trying to say, okay, could there, it's exposed to the air.
It's actually quite common, and those calculations have been done, and I'll try to point you to them later. I didn't have, but it is quite common. But the big thing, here's the most important part though. If you see those papers that supposedly report radiocarbon ages for dinosaur bones, whatever kind of material, look at their ages. They vary by several half-lives of carbon-14. So how could that be if they're all supposed to be around the same age coming from the same atmosphere? That should be the first clue. If you have a single dinosaur bone and like different elements within it are giving different radiocarbon ages, not just different radiocarbon ages, they're off by several half-lives from each other. That alone tells you that anything that you're measuring, any kind of radiocarbon that you're measuring in there, did not come from the dinosaur bone. It came from anything else than that. Otherwise, they would give consistent ages, and they don't.
No, that I would agree with that. I would agree with that. What Lowe had proposed, and I mentioned it in passing, the 1989 paper, he was saying that there was in situ contamination or bacteria. But one thing, but he was saying that he felt that the in laboratory and then the trans process did not add the contaminants. He felt it was in situ, not through the processing. And I said, that actually makes sense. And I would welcome looking at the numbers you have, and then I'll compare it with mine.
Yeah, sure. But you also got to consider the geological context and the different sources of contamination. So if it's something like a bone material or especially a permineralized bone material, there are a number of new sources of contamination that were not possible when we were talking about diamonds. That's why those materials can give much younger apparent radiocarbon ages than something like a diamond.
I was thinking, okay.
And the modern carbon contamination, it doesn't just come from exposure to the atmosphere. It comes from exposure to groundwater and microbes and all sorts of other things.
Yeah, so it depends on how, I guess, for lack of a better word, how porous and how things can flow through it. And also, like, people have cited bacterial contamination. Well, that would make sense if the bacteria are coming in and going out, the waste, because if the bacteria just lodge in there and never get out, they have a finite age too.
Yeah, well, it's also the residual organics from the decay of bacteria and plant material. That's what gets in there and gets stuck to it. And also the actual mineral, the carbonates, anything with a carbonate structure can get replaced by carbon that's in the groundwater, like modern groundwater, and then it gets replaced and exchanged. So now you actually have 14C that's intrinsic to the mineral structure, but it didn't come from the original organism. It came from modern organisms and it got exchanged chemically in there. So those
it's basically it's flowing in and out. It doesn't get stuck. Okay.
But at the end of the day, like we do know, without any reasonable doubt, we do know that radiocarbon dating works pretty well back to 50,000 years by dating stuff that can be independently dated, right? Where we independently know the age of the sample. And that's quite feasible to do back to 50,000 years using lake sediments, tree rings, speleothems, corals, etc. And that would not be the case if there were this big problem with radiocarbon dating that was complicated by, say, a recent flood or catastrophe or anything like that.
Well, I have to contest that because that is circular reasoning that the 50,000 year date is accurate to begin with.
Well, what I said is it's independently known.
How do we know that method is correct? I mean, no one was around. I'm just saying, no one was around 50,000 years ago.
Well, depend which method are you talking about? I mean, because we can. We've got five different. If you have 5 different methods that give the same results.
Well, how about it could also be attributable to confirmation bias.
How's that? Like what confirmation bias here would cause 5 different methods?
How about anything that's how about data points that would show that would show something that's, because I gave you the ones with collagen, and that was dismissed. I could just as well say that that's accurate. Anything with 34,000 or these clamshells with 24,000. So we're going to take
Well, you could,
we're going to
but
take
then
the
you have to
numbers
be
that
able to
we
show.
like and then throw out the ones we don't like. That's what I have a problem with.
Oh no, it's not arbitrary here. I mean,
Okay.
if you want to say that that's intrinsic to it, then you've got to show some reason to think that it's actually intrinsic.
Okay.
And what I'm saying is that there are a million other reasons to think it's not in
Okay.
other sources it could have come from. So why think that the least likely reason happens to be the true one? The least
Okay.
likely reason is that it came from
Right.
that this radiocarbon came from the dinosaur itself. That is the one that's most
No,
least likely
well,
to be the case.
I'll tell you why I suspect the dinosaur has in a lot of ancient biomolecules look young from a chemical standpoint. Racemization, oxidation state, any number of things. Those are also good clocks too. They won't tell you the accurate date of when, but it will tell you what date it can't be, and it can't be millions of years old. I've seen papers that said we'd have to re-understand our idea of chemical kinetics, and I'm like, maybe the dating of the fossil record is the problem. Your chemical kinetics is valid, and that's why I'm just like, okay, we have both sides making good arguments, but I can't just dismiss what I see from the chemistry too.
Mhm.
I mean, racemization, I've been looking at this. I actually found it, no one wants to do this, but there was a paper in the 60s that said they found unracemized things in the Cambrian. And that paper has been obviously, they're just saying contamination, this or that. And I'm like, okay, time out, And then when we found these fossils here that have chemical dates that look problematic. So I can't just say that the carbon-14 is an outright anomaly. We have these chemical dates too. To me, that would supersede the tree ring counting because chemistry has precedence over tree ring counting.
I don't see, no, I wouldn't say that at all. How could have you gone through the radiocarbon calibration curve and how that's made? And do you know what I was referring to when I say you got several?
Yes, and I thought those are fairly credible, but I would like to review them again. But again, I'm looking at, we have these anomalies that haven't been explained in terms of chemical kinetics.
Mhm.
And some very fine chemists, including
These
James
are different
Tour.
levels of confidence here. When you're talking about the chemical kinetics, that's where you really don't know the conditions under which that applies. And so you could say, yeah, it applies in this system under these conditions, but you don't necessarily know the conditions, the history of.
Well, I looked at the ways, there are many ways to accelerate, like say the decay, the chemical decay, very hard to slow it down. Mm-hmm. Each time I looked at it, it's like you freeze it, you could change the pH, but these all accelerate the decay. There are limits to how much you can slow it down. And everything I've seen, so we're actually having to invoke exceptions for biological systems to say, okay, why are the amino acids in a non-racemic state after supposedly millions of years? That doesn't make any sense. Mm-hmm. All of our experiments say we can accelerate it by heating it. We can change the pH, but that usually accelerates it one way or the other. There's kind of a baseline pH from which you're not going to get it to slow down anymore by fiddling with the pH. You could throw other chemicals in there. Mm-hmm. And so I'm just saying, I think the case is still open there. And what would look really bad is if you have it, there's not that much variation between strata. And that's what I would look at.
Mm-hmm. So yeah, the two things I would point out there, one, we have a lot lower confidence because the one assumption that goes in there is that the materials you're looking at are, again, intrinsic to the sample and not any sort of contamination in the preparation process. Okay. Yeah. And the other thing is if we go with that and say, just like that alone, we know it's much younger than we thought it was from the geological record, you're throwing out a lot of, thousands of independent data points that corroborate this. And you're throwing out everything. You have to throw out all of geochronology. And that's where we have much higher confidence because we have independent corroboration. We have ways to objectively test this. And
Okay.
you don't have that with what you're referring to. So it is an open question. That's fine. And it's exciting because it's an unexpected result, to be sure. So I'm not going to pretend like that's a closed case that we shouldn't study that anymore. But as far as I can tell you more about the geochronology and like how that calibration curve is constructed. For example, we date something using uranium, thorium, and using radiocarbon because it has both of those elements in it. And when those dates line up perfectly, systematically going from younger to older, that's how we can be confident that those radiocarbon ages going back to 50,000 years actually go back 50,000 years. And when you realize that, just scratching the surface of Earth history is at least 50,000 years old, the whole, the rest of that point kind of becomes moot. So yeah, I mean, sure, you could say there's some flaws in tree ring counting. You could say there's some flaws in counting of glacial ice or counting of varves in lake and marine sediments, or even dating corals and speleothems and stuff like that. But when all of them give you the same result about the radiocarbon history, it becomes very difficult to throw that out.
Were there any, well, if there were studies that would contradict that, have there been any studies that contradicted that were not published or welcome to be published?
Well, contradicted it how? Like a comprehensive, because the calibration curve at this point has thousands of samples in it that corroborate. So, I mean, if you know of one that gives the opposite result, then sure. But you'd have to show why that one result that contradicts the thousands is worth accepting over the thousands.
Like the dinosaur bones.
That doesn't contradict it at all, though, because then you just have a single date of a substance, which is very hard to process by itself. And you have, 10 different sources of carbon in there, and you're arguing that it only can come from that one and not the other 9.
Or the clamshells or
yeah, same thing.
If you from the Cambrian.
Though,
see, that's what I'm saying here. Is
if you understand diagenesis in carbonate systems, that's not surprising at all. And so it's not a data point you would even say contradicts the other stuff. It doesn't contradict it at all.
Well, see, that's what I'm saying is you can look at these data sets and pick the ones that give you the story you want to hear. And that's what I'm getting from this.
It's not arbitrary,
you're gonna get the ones
going through the test that.
Right.
If it were arbitrary, we're not just picking the ones we like.
I'm just saying that this, that's where I'm saying that there could be confirmation bias here.
Yeah, no, you're absolutely right.
You can pick all these
studies
studies that you'll say are independent, throw out all the data points you don't like. You'll say, okay, these are really good. They all agree, and therefore it's reliable. And then you can ignore all the other data points. You can try to explain them away. Mm-hmm. And that's what I'm having a problem with. Now, just to give a little background, when I was going through school, the Big Bang was the major paradigm. But I always, as I matriculated through school, I noticed the whispers among graduate students, young professors, even some of my professors that were skeptical. And now the skepticism it's becoming a little bit more open. And I'm like, yeah, I've seen how we could have such a strong consensus and then the anomalies are just resisted. Everything looks consistent if you look at only the things that are consistent. Mm-hmm. And that's why I'm a little bit more sympathetic now. If I hadn't seen all of this overturning, and then the same thing with abiogenesis for sure, where it looked like it was a go. And then I look at the literature 40 years later, and it's a failing paradigm. So that's why I'm a little bit, it's driven my skepticism a lot. I'm not saying that the scientists are dishonest, but there's a kind of like it's hard once you get into a certain, a lot of intellectual investment in an idea. It's just really hard to let it go.
That I get. I won't comment on those other theories. I can't speak to them from experience or expertise of any kind. When it comes to this, the comment about picking and choosing what you like, it doesn't describe what's going on here. Just because we can show objective methods by which to determine what high quality data are, what low quality data are, where you have high and low confidence. And if you're taking like radiocarbon dates of material that theoretically should have no radiocarbon in it, that has 1,000 different ways to contaminate it or have a raised background level, and those are single dates with no independent corroboration of the age, that's not a strong data point to contradict everything else at all. In that case, you've got 100 different ways to explain why this radiocarbon date or apparent age is what it is, and you want to choose the one that's the least likely and that happens to contradict the other thousands of data points around. And so that's not what I would call picking and choosing what we like. We're picking what the preponderance of evidence is, and we'd consider the other things anomalies. Anomalies are always worth exploring, and it's helpful to challenge our paradigms. I'll give you that. And I think the most interesting part of this has been, this is why I study and still study kind of young Earth creationist claims, because it's fun to work through those anomalies and to see how people are looking at anomalous data and thinking that they would overturn the paradigm. And that's a nice challenge to go through. But it's logical to stick with the preponderance of evidence until you have reason to explain it the other way, right?
So you did say that. Does that mean we can date certain trees to about 45,000 years?
Well, actually, yeah, you can. But using the tree rings is helpful, because if you have a tree, like you cut it down today, you know that the outer ring is about a year old or less, right?
Okay.
And then the second ring in is 2 years old, and the third ring in is 3, and so forth. And this is how we construct the chronology and test it, because with tree rings, you can link up those chronologies with the rings all the way back at this point to like 13,000 years in Scandinavia. And if you date those individual rings, which are dated first by counting them back in time, and secondly by radiocarbon, that's how you have independently corroborating methods. Now, you could say either one of those is flawed or has its problems or assumptions or whatever, but when they corroborate each other, then you've got a different story. It's the same thing like with speleothems. It's very, that's what I do, by the way, is date speleothems. And in that case,
pardon my ignorance, what are speleotherms?
Speleothems meaning secondary cave formations like stalagmites.
Okay.
Because
we have someone here from the Middle East. I don't know that she was ever in Istanbul, Turkey, but just saying, John here had traveled. He just came back. He's really sleepy and tired, and I'm very grateful he came here to talk. And so he gets to travel all over the world to examine caves, which is just really cool.
And yeah, that's getting complicated right now, because I was supposed to move to Russia in 3 weeks. That was my original plan. That just fell through.
I shouldn't laugh at tragedy, but it's
it's pretty difficult time, as you mentioned, and that's all around.
Audience, sometimes when something is just so bad, I can't help but laugh, because I'm not trying to be. I'm not being trying to be.
The last few weeks, it's just every day read the news, and it's almost I don't know how else to describe it. It's like it doesn't seem real, right? And because every new development has been like, wow, that was unexpected, and now I got to readjust. And then the next day, oh, that was unexpected, I got to readjust. And so that's kind of been how things are going right now. But that's okay. I was just mentioning we date speleothems using uranium and thorium method. That's pretty cool. I'd be happy to go through it sometime and explain why we know that is extremely robust. You're not dealing with the same issues like contamination that you are with radiocarbon. You're not detecting something that's extremely, extremely rare isotope like 14C is. These are far more abundant, much more easy to check the assumptions that go into radiocarbon. The assumptions that go into radiometric dating can easily be checked with this system. So it's much more reliable. And that's why I would say you can't, to say that you're overturning that because somebody claims to have dated collagen in a dinosaur bone and can't replicate those states within even a half-life of radiocarbon, that is suspect to me. And I will stick with the one that that can be tested, corroborated independently, even by people from across the world, different faiths, different political backgrounds, everything getting the same results.
Uranium. Okay.
Yeah, so uranium thorium is a very excellent system, and
does
that's
that mean that you're
system.
going to be? Are you? And I'm sorry to impinge on you, but if you can't go, did you actually have your tickets and hotels lined up for Russia?
Oh no, that's fine. I like, just for some background, I've lived in Russia for several years over the last decade, and most of my work is there, colleagues, friends, everything. I'm not technically cut off. I think I could still travel there if I wanted to, but
given what they did to the basketball player, I would just, I mean,
yeah, I'm still working in the region though, in that area, but.
Well, let me just say this: even if you're a good guy, Putin has imprisoned people. They like to imprison people and hold them hostage. I'm just okay.
No, yeah, don't worry. I'm fully aware of what's happening there. I'm not gonna be going back anytime soon, which is quite unfortunate because I've got ongoing research there, projects in place, samples, everything, and so this is a big interruption to that. But
well, there was a selfish reason I was asking you.
Mm-hmm.
Would you be? Does that mean you're going to be stateside a little longer, or do you?
I'm going abroad, but just not there. I'll be in Europe instead.
In how long?
In a month or so.
If you would like, I will not interrupt you as much as I have tonight.
No, I don't think you interrupted me at all. I'm totally fine, and I hope I didn't interrupt you going back and forth. But I'm happy to come back and continue the conversation if you like.
If you want to talk about uranium thorium dating and the independent carbon methods, I'll give you free rein, and I'll tell you why. This will not be different. There are a number of young Earth creationists here on the channel that are science students, some even biology students, graduate level. This will not be different from them going to secular school. This is, I went to a secular school to study physics. So, okay. I studied astrophysics and cosmology. I had to learn, still don't know how I did it, but I had to learn to just say, okay, I'm going to give them my full attention, and I'm going to make the grade, and I'm going to try to learn this. Even if I have my reservations, this is going to be an education. So I think the audience would be very, very privileged to hear you speak, and to teach it the way you'd want, because it'd be irresponsible if I didn't give the other side a very, very fair hearing. And then it also will teach the young Earth creationists there to maybe not be like the guy who dresses up in a Superman outfit and advertises himself as standing up for something. I do not agree with that at all. To say, to pretend that we have such an airtight case, and then they would have to face someone like yourself or study with a professor like yourself teaching them. I said, this is not the way to prosecute young Earth creationism, because you're going to just look stupid. You have to respect the other side. Now, abiogenesis and eukaryotic evolution, it's a different story for me, because when I've discussed this with the opposing side, I don't think that they have veiled themselves as well as you have tonight. So I think,
well, those are much more difficult fields. I'll grant that. I mean, if you're a scientist studying that is still within the realm of. It's always going to be in the realm of conjecture, because it's going to be so hard to test.
And that's why I would, yes, And that's why I would say that's faith-based. They resent me saying that abiogenesis is faith-based. They would resent me saying that problems with not common descent, but protein evolution, which is my specialty, and eukaryotic evolution. I just say, guys, it doesn't line up with anything I know about chemistry, genetics, cellular biology, etc. I usually, if anyone watched James Tour's abiogenesis series, they'll know what I mean. He walked over the other side pretty easily. But I keep telling people, I said, criticizing complexity like that of the cell is easy. I say intelligent design is easy. Young Earth creationism is hard for the reasons you've outlined tonight. And I'm like, well, I think you've made very, very credible points. And it doesn't justify people on YouTube getting up in a Superman outfit and just like pretending they can just refute people. So,
yeah, I understand. Kind of understand the mentality. I've met a wide range of people on either side who can be arrogant of all sorts or willing to learn everything in between. I've spoken with even folks at staff at Answers in Genesis and other places, and you see a wide range of personalities. I'm not going to comment on anyone in particular here, but I'll just say, like, I know what you're talking about, and I'm very appreciative that you're lending me your ear. And
no, they should hear you, because people have been criticizing me and say, Sal, you're a turncoat. I'm just like, no, I'm not. Do you know how hard this is? Do you know what you have to learn before you pretend you've solved this? I mean, I will mention one person, and that's Kent Hovind. He's been convicted felony counts for tax evasion, convicted of domestic abuse of his wife and Cindy Lincoln in particular, and she's been on this channel, married 4 times. Now, for a Christian, that, all right, someone outside the church, I'm not going to pounce on that. But if someone is representing themselves as a minister of the Christian gospel, they're married 4 times in the last 5 years and are convicted of domestic violence against their wife, that just doesn't cut it. I will mention Kent Hovind specifically.
Well,
if he's going around pretending that this is easy, that's the wrong message to send, especially science students. I'm sorry, I interrupted you, John.
No, that's okay. I was just adding to what you said. I think it's anti-evangelism at that point.
Yeah. So, and I feel really bad for Jordan.
I'm so sorry too.
We did, well, Jordan, you're the one who invited John. See, this is what happens when we get. Jordan, I didn't want to I wasn't trying to monopolize away from your fine work, and we'll probably talk in the emails and backstage. So, John, I will roll out the red carpet for you, and I will not. I'll endeavor not to interrupt you as much as I have tonight.
I enjoy the questions and the back and forth. You got some good point and good questions, good things to talk about. So appreciate it.
And so whatever you say, Sal. Well, Jordan, while I have you in the side chat, would it be okay while John is in town? Jordan will be out of pocket for a month anyway. And John's here. If you'd like, could we, I know you're just dying from jet lag and changing your clock, but I'll clear my schedule for you. I would love to have you talk about uranium, thorium.
Yeah, sure.
For starters, is there a day of the week, a time of day that works for you?
Any evening is fine. I teach till the afternoon, so any time in the evening is great.
Okay, I'll contact you in the back channel to work this out. And so, guys, the regulars to this channel that know that we do advertise young Earth creationism here, this is going to be some tough medicine for you guys, all right? Because you're going to hear a viewpoint is in opposition, but I feel that it's my responsibility to say, you got to listen to this. You got to hear the other side, argue their case. They need a fair hearing. And particularly the science students, if you're going to matriculate through school, you're going to have to face stuff like this. It'd be better that you face it now than when you're in school and you don't know how to handle it. So I'll contact you backstage, and I'll invite Jordan too, but I'll yield the floor to you, and that's a very kind of you to offer that. So I don't. We're already at an hour and 47 minutes. I really thank you for your time. As exhausted as you are, goodness.
It's easier to adjust back this way than going there. It's okay.
Okay. So as I said, I think the case for intelligent design is easy in terms of not proving the designer, but proving the complexity of life. That's arguing the difficulty of evolving it. And the secular sources themselves now are saying, you know, they're invoking multiple universes as explanations. I said, okay, that tells me something, but I still stand by what I said, that young Earth creationism is a gigantic thing. It's, you know, for some of us, we'll accept it by faith. We don't have as many facts in hand, definitely, as we'd like. And part of me trying to convey that is inviting people like Jon, and you know, and this is also highlighting areas that the community has to get better at. And we're talking about the experiments we need to run, and you know, maybe the caveats we have to add to some of our scientific papers, etc. So I'll give you the last word, Jon, and I'll meet you briefly backstage.
All right. Well, I appreciate it again. I think it's important to note, just since we talked about radiocarbon, that it's a very difficult technique, mainly because 14C is so rare in the atmosphere, and the instrumentation we use is extremely high sensitivity, and there are lots of little correction things that you see that you don't see that happen backstage in that system. So I think when you study the geology and the actual lab analysis part of it, these sorts of anomalous dates that are touted by young Earth creationists as, you know, evidence that we should throw out the rest of geochronology, I don't think that is that's not the best approach, you know. So if you got 1,000 ways to explain something and you pick out the one that contradicts the preponderance of evidence, that's not a good way to do science. That doesn't mean that's not true and that we can't learn something from it. And that's why I'm happy to keep talking about those anomalies and such. But I just wanted to make clear, like, radiocarbon that's the most problematic, I think, of the geochronological methods. You can run into the most complications and such. And that's why we tend to avoid it if you can use anything else. So we'll talk about uranium thorium next time, and hopefully show you why it's much easier to deal with, much more reliable system.
That sounds great. And I'd like to thank everyone for joining us this evening, and a special thank you to Jon, and thank you, Jordan, also for joining earlier. And he's the one who lobbied to get you on tonight. And so thank you very much, Jordan. And I'm glad we finally connected. And thank you very, very much for your time, Jon. I'll meet you backstage. Take care.